Welcome to homework.
So here in this problem we are given that there is an insulated piston cylinder device which contains 5 liter of saturated liquid water. That means the volume it is given as 5 liter, and if you convert this thing into meter cube we'll get 0.005 meter cube, and the pressure is 150 kilopascal. It is given in the equation. And then electric resistance heater is turned on and it transfers 22 kilojoule of energy to the steam, and we have to find the entropy change of the water during the process. So to solve this question, we'll be using the steam table A4 and A6 that is given in the book. So the initial condition it is given P1 it is 150 kilopascal, and the state is saturated liquid. So we'll be using the table A4 to calculate the specific volume at state 1, and specific enthalpy at state 1, and specific entropy at state 1 at pressure 150 kilopascal. So it will be 0.001053 meter cube over kg, and H1 it will be from the table it will be 467.13 kilojoule over kg, and the specific entropy will be 1.4337 kilojoule over kg Kelvin. So this is specific entropy. Now next we'll be calculating the mass of the water. So M it will be volume divided by specific volume at state 1. So volume we are given as 0.005 meter cube, divide by specific volume we have obtained as 0.001053 meter cube over kg. So after solving this we'll get the mass of water as nearly 5.75 kg. So we have calculated entropy at state 1, and next we'll be calculating entropy at state 2, that means after transferring 22 kilojoule of energy to the steam. So for that we'll be first balancing the energy, that is energy input minus energy out. It will be delta energy, change in energy for system. So we have balanced the energy. Now energy input we have work input, and there is no other energy that is moving out, whether in the form of heat, because it's an insulated cylinder, and delta of change in energy will be m times H2 minus H1. So from here H2 will be equals to H1 plus work input divided by mass. So we have all the values here, we can plug it here to calculate the enthalpy at state 2. So H1 we have obtained as 467.13 kilojoule over kg, divide by, sorry, it's not divide, it's plus, work input is given as 2200 kilojoule, divide by mass. So mass we have 4.75. So after solving this we'll get the enthalpy as nearly 930.33 kilojoule over kg. Now next I will be calculating the entropy at state 2. So in the equation it is given that the pressure remains constant. That means at state 2 pressure P2 it will be equals to P1, and that is 150 kilopascal, and H2 we have obtained as 930.33 kilojoule over kg. So now again we'll be using the table, and from that we'll be calculating the quality of water at state 2, that is X2, and then we'll be able to calculate S2. So X2 is equals to H2 minus HF divided by HFG. So H2 we have obtained as 930.33 kilojoule over kg, and HF corresponding to pressure 150 kilopascal. From the table it will be 467.13 kilojoule over kg divided by HFG is 2226 kilojoule over kg. So from solving this we'll get the X2 as 0.2081. Now this specific enthalpy at state 2, it will be SF plus X2 times SFG. So SF from the table, it will be 1.4337 plus 0. This X2 is 0.2081 times SFG is 2.6384. And after solving this, we'll get the specific entropy as 2.6384 kilojoule over kg Kelvin. Now we can calculate easily, that is the change in entropy, that is M times S2 minus S1. So M is 4.75 kg, S2 we have obtained as 2.6384 kilojoule over kg Kelvin, and S1 we have obtained earlier as 1.4337 kilojoule over kg Kelvin. So after solving this, we'll get the entropy as 5.72 kilojoule over Kelvin. So this is the final answer. I hope you got the problem. Thank you.